Hello, everyone, and happy St. Patrick's Day. Thank you for joining us today, and welcome to MEGR's monthly webinar series. Today's topic is battery testing and maintenance as per NERC PRC-005 guidelines. My name is Jamie Smith, and I'm the Digital Marketing Specialist for MEGR North America, and I'll be acting as your moderator for today's presentation. I'll be supporting you on any technical issues or questions for our presenters and panelists today. On the right side of your screen, you will see a control panel that looks similar to this one. You could submit questions at any time during the presentation by typing in the box highlighted in red, and I will read those questions out later during our Q&A segment at the end of the webinar. And just FYI, all webinar attendees will receive one PDH or 0.1 CEU just for attending today. You will receive this in an email within about 2 business days after the webinar ends today. That email will also include a copy of the PowerPoint presentation and a link to the recorded video of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered after the webinar ends. We'll have a 30-minute Q&A session. Okay, and our presenter today is Volney Naranjo, and he's our Senior Applications Engineer for MEGR. Also joining Volney at the end of the webinar as part of our Q&A panelists are Robert Foster, MEGR Applications Engineer, and Andy Sagel, Battery Product Manager. Okay, let's go ahead and get started. Thank you for joining us today, Volney.
Thank you, Jamie, for the introduction and the presentation. Well, thank you also, everybody, for attending this webinar. If you feel alone, you are not. Right now, we are reaching the 500 attendees, and we have 1,000 registered people. So feel free to ask as many questions as you want through the webinar system. We'll be answering those at the end. It will be an interesting discussion if you ask several questions, so you're welcome to participate. So we are here today to talk about battery testing, and there's a main reason for that. The batteries are the heartbeat of a substation. Nothing works in a substation without a DC system, and they just sit there and they are expected to work in the critical moments, and if they don't, the critical situation can turn into a serious problem. However, batteries die very easy, or die easy, and they can die fast if we don't properly maintain them. And despite this, they are usually disregarded or assigned a low priority, probably because they are easy to obtain or they are not so expensive as any other big or important element in the electrical system. So there are many technical reasons to keep these batteries well maintained, to keep a close eye on them, but the most compelling reason nowadays is the enforcement and the fines. And fortunately, we have this because that is the way to avoid serious problems or avoid an unfortunate series of events like what happened in 2003, where we had a big blackout where 50 million people were without power, and can lead to a catastrophic situation. So that's why we have put together this agenda today, to illustrate you on what is enforced, what is required, and what other tools you have to properly maintain the batteries, and to provide a kind of a comprehensive information for you to start working on that, or keep working on that. So we have this agenda. We're going to be talking about NERC. We're going to be talking about PRC 005-6, which is the standard that includes the battery testing, and the required testing schedule in this standard. We're going to see other resources like IEEE or NETA, a quick comparison or a quick reference list. And mainly, we are going to be talking about the electrical tests that are required and the best practices, with final recommendations, and then the question and answer session. Okay, so For starters, NERC, well, NERC is the North American Electric Reliability Corporation. It was designated in 2006 by the Federal Electric Regulatory Commission, FERC, as the authorized or the authority that develops reliability standards that are applicable to the US and parts of Canada. These reliability standards define all of the requirements for planning and operating the electrical bulk power system, just to have the system always operating and avoiding any issue. And it doesn't cover only batteries. It really has 14 standard families, and within those families there are many documents. The one that talks about specifically about batteries is called PRC 005. And as we're going to see in further details, that is not only for batteries, it's for other, it's for the protection system, but it includes the batteries. One very important thing about this NERC standard or regulation is that they are enforceable, and they can even fine the company for violating these requirements. So they can ask you to rectify any issues, or they can fine you up to $1 million per day per violation. This is depending on a table that I'm showing here, and there's two criteria to define the fine. There's a violation risk factor that you can see on the left column of the table, and this is the expected or the potential impact of the violation of our requirement to the reliability of the bulk power system. It's basically a pre-violation assessment. So each requirement will have a certain category of violation risk factor, and once the requirement is violated, it will be evaluated by the authority to determine if it was a lower or moderate or high or a severe violation, but they are also pre-established already, and within that established level you have a range, and that from that range is that they will define the money that you need to pay for that violation per day. And batteries are already pre-located, or they are already defined in the severe limit or in the severe level for as a medium violation risk factor. So any violation to this standard from or related to batteries will represent a fine in between $10,000 or up to $335,000. So this is, again, one of the compelling reasons for all of us to be here and to be sure that we can avoid all of these issues. Going into the details of the standard, well, as I said, that the standard is called PRC 005. It has passed through several versions or revisions. The one that is enforced and is current or effective right now is PRC 005-6. The previous one was 2I, but that was removed, or that was superseded by this one like a year ago. So the purpose in this document or in this standard is to implement or to ask electrical companies to document and implement a maintenance program for all of the protection systems that will have an effect on the reliability of the bulk electric system, with the purpose to keeping them in working order. So the document also defines who needs to comply with this. The owners of transmission and generation, they definitely need to comply with these if they are connected to the bulk electric system. And some distribution providers, especially those that have under frequency or under voltage load shedding protection, they also need to comply with this. Now there's other criteria there more specific criteria. These are like the general criteria. There's one specific criteria that protection system facilities that work on systems of 75 MVA up from 100 kilovolts or above. So there's some specific details. Obviously, this is covering just the basics, and we encourage you to review those documents to be more informed about this. Moving on into the details of this standard, there's 5 requirements in the document, and they are called with R and the number R1 to R5, and the one that covers batteries is R1, and it's just one small part of that requirement. Before getting to the details of that requirement, it is important to mention that the standard also includes compliance, a chapter which shows who is the enforcement authority, how you need to keep evidence of the testing, or how do you need to organize that information, how the compliance monitoring assessment process will be. And it also has this table of violation severity level, what I was mentioning before in a previous slide. And here you can see that I have highlighted the importance or where the batteries are assessed or already evaluated as a severe violation severity level. So the entity's maintenance program failed to include applicable station batteries in a time-based program, which is part of the requirement. So this is a screenshot of the standard, specifically of the requirement that we're talking about. Again, this is the main requirement is that the entity shall establish a protection system maintenance program for all the protection systems, including automatic reclosing and sudden pressure relaying. These 2 last items were one of the additions in the latest revision. Before, those were not included. And here you can see that this is qualified as a medium violation risk factor. So the previous slide and this one shows you where the batteries are located. So one sub-item of this requirement is that the battery systems shall be included in a time-based program, and they should be the program is already established in tables 1, 4, and table 3. Now, one thing about this standard and these requirements is that for any other thing any other system or element covered by this standard, they have the freedom of leave you the freedom to decide if you want to do a performance-based maintenance or if you want to do a time-based maintenance, or you can do a combination of both. However, for the batteries, it is already established that you need to do what they indicate in this standard. So on certain way, it's pretty easy to follow. You already have there what it's required and its minimum requirements compared to other standards. So the main thing is to review these tables, this time-based program, which was developed based on regular standards that the industry has for battery maintenance. So table 1.4 is really like 5 tables. They go, or 6 tables, they go from A to F. And the very first table, table A, 1.4A, is for vented lead acid batteries. Here we can see that there's 3 periods in which you need to perform maintenance. And the very first one is every 4 calendar months. Every 4 months you should verify the station DC supply voltage. It's a basic multimeter measurement. Then you need to inspect the electrolyte levels. Lead acid batteries, vented lead acid batteries, they are in clear jars that you can see through, and you can determine what's you can inspect them and you can see what's going on inside the battery, and the electrolyte level is one of the most important. It evaporates with the battery operation, and you need to keep those levels up and within the specs. And another inspection that you need to run every 4 calendar months is to inspect for an intentional ground. So DC battery systems, they are floating systems. They are not supposed to be grounded. Any ground in the system will cause current circulation, which means that the battery is operating, and this is not good for the battery. Batteries in substation applications, they are meant to be sitting there. They don't like to work. They're just there for very special occasions. So you don't want the battery to be draining current through ground. So this should be inspected. And all of this should be documented. It's not just going there to the substation and verifying that everything's fine and then you go home. No, you need to document this, and this has to be properly archived and maintained in a database system that you can show whenever NERC comes to do audits, because that's how they will find out if you're following things or not. And audits is the main thing with NERC. They want to see that you are doing the job and that you are maintaining your system. So 4 calendar months, very basic measurement. Then every 18 calendar months, you do again a voltage verification of the float voltage of the battery charger. You also need to verify the battery terminal connection resistance, a basic low resistance ohm meter or digital low resistance meter, to verify this. Also, you need to verify that there's battery continuity. You want to be sure that the battery is not open or is not short-circuited. So a basic multimeter measurement as well can give you this value. It's just a confirmation that there's a circuit across the battery. And this is also verified with, confirmed with battery intercell or unit-to-unit connection resistance, basically a strap resistance measurement. And it's also a very basic measurement, but it's very important because it will give you very important information about the condition of each cell, or if you are probably causing a problem on a specific cell. Then they want you to inspect the condition of all the cells where they are visible. As again, they are clear jars, so they must be visible or pretty easy to inspect. But sometimes, depending on the installation, you are not going to be able to see those through them. And so they offer you the possibility to perform ohmic measurement of ohmic values, which is one of the electrical tests that we're going to be talking in detail here, because it's one of the important tests, electrical tests here. You also need to inspect the physical condition of the battery rack, and this will cover all of your 18 calendar months inspections. Then there's another requirement, that you need to verify that the battery is capable to operate as per the manufacturer specs. Batteries have certain spec, they have certain capacity, and that's what everything is based on. All the backup that the battery can provide is based on that capacity. So NERC wants you to verify that the battery is going to meet that requirement. And there's 2 ways to do it according to NERC. There's you can do an inspection of the ohmic values again every 18 months. And if you or if you don't want to do that and you want to do a different test, you can perform or run what is called a performance test or modified performance test, which is also known as a discharge test or a capacity test. So this is something that you need to define when setting up when preparing your maintenance program. And once you decide what you are doing, you need to keep doing it. And probably I don't have details on what if you want to change the method, but you need to keep documentation of all of these tests for the audits. And this discharge test can be done every 6 calendar years. I guess, I don't know if I mentioned that, but so you can do 18 calendar months of internal ohmic values, or a discharge test every 6 calendar years. Okay, the next table is pretty similar to the previous one. It is for the valve-regulated lead-acid batteries, VRLAs. You have the same schedule, 4 months. Well, you have one more period there, 6 calendar months, 18 months, and then you have the verification of the capability of the battery to perform as the manufacturer's specs. In these batteries, you don't have clear jars. You have a jar. Usually they are I don't know, depending on the manufacturer, gray or orange, or well, so you won't be able to see through the battery. The electrolyte is still lead acid, but it might be in a form different than a gel, so there's no different than a liquid, so you really cannot inspect the electrolyte level. So that's why it's not in the 4 calendar months inspection. And because of this, because you can't see through the jar, you need to use another method to try to determine what is going on inside the battery. So that's why this table includes the 6 calendar months, asking for internal ohmic values. So this is a requirement to perform every 6 calendar months this type of test on these batteries. And every 18 calendar months, you have basically the same verifications or the same measurements as for the lead acid batteries. And if you take a close look to those, mainly is to verify that there's a good operating circuit through the battery. 3 of those tests will confirm the same thing, that you have a continuity, that you have a good path for current to flow through the battery. And then you have also, there's the requirement to verify that the battery can perform as the manufacturer specified. And again, you have 2 options. You have the ohmic measurement every 6 calendar months, or a discharge test every 3 calendar years. The periodicity is lower. You have, or it's higher. You have, instead of 6 years, every 3 calendar years, because again, you can't see through these batteries and they might deteriorate faster. And one important thing to highlight here is that if you do the calendar, the discharge every 3 years, it doesn't mean that you don't have to do the internal ohmic values. You still need to do the internal ohmic values every 6 months, but whenever you hit the 3 calendar years, that's when you have the option to run the discharge test or keep doing an ohmic test. So in these batteries, you need to do both tests, the ohmic and the discharge test. Okay, the next table is table 1.4c, and this is for nickel cadmium. These ones are also batteries that use liquid electrolyte. You can see through the jars, so you are asked to inspect the electrolyte level and the same other 2 inspections that are required for the calendar month, for the 4 calendar months. The same 18 calendar month schedule of testing. And as you can see, or the point to highlight here is that in this one, no ohmic values are required. The reason is that NiCad batteries, they behave differently. The electrolyte that they have is as alkaline. This material is not dissolved in the liquid. It's mainly in the plates. So you really won't see any ohmic value change throughout the life of the battery. and you might see a big change at the end of the life of the battery, or you might not. So really it's not a very good indicator of the condition of the battery, so that's the reason it is not included in this table. As I mentioned, there are more tables. There are other tables, um, D, E, and F, and table 3, but those are mainly for DC systems that don't have batteries, or that they just ask for a basic voltage measurement at the protection system. So no really focus on the batteries per se, but more on the DC system. As I mentioned before, there's other resources. IEEE and NETA standards are the main resources for battery testing recommendations, and NERC mainly took all of the recommendations of all these requirements from these standards, and obviously they are going to be more comprehensive. There's IEEE standard for 450 for vented lead acid batteries. It's standard 450. For valve regulated lead acid, it's IEEE 1188, and for NiCad batteries, that's 1106. So, and we here in MEGR, in the technical support group, get a lot of questions, always trying to people want to know what they need to do on the battery, what's the minimum, what's more comprehensive, what is kind of the premium maintenance program that you can set up. So to facilitate at least to understand and to know what things you need to do, like for a quick reference, we prepared a table that will give you a very fast understanding of what is required for each on each document. So we have a list of activities, all of the activities listed in all of the documents, and in front of each activity we have how often it is required and for what type of battery is required, and which standard requires or asks for it. And the way we identify each of the documents is IEEE standards. It's identified with an I. The N will indicate NETA standard, and P will indicate the NERC requirement for PRC 005. So this is the table. Of course, here is a little bit jammed, but we can provide these tables and kind of more detailed tables or easy to read tables if you contact us. This shows, for example, the float voltage measurement at the battery terminal. So you can see here IEEE requires that for vented lead acid batteries and valve regulated batteries. Monthly, and obviously triannual or quarterly, and NERC, as we were saying, it requires that every 4 months. It's also required in NETA every 18 months or yearly. Yearly. So this table will indicate you pretty quickly what are the requirements in all of the standards, and of course there are some notes. You can see some numbers here associated to one standard. So we have a table with footnotes, and for example, for this previous one, cell-to-cell terminal connection resistance, it has number 6. That is that only one of the 3 actions is required. So in NERC, sorry, in NETA, for example, to verify the continuity of the battery, they ask only for one action. NERC asks for a cell or a strap resistance measurement, the battery continuity, and also one additional action there. So this will help you a lot, and as I said, we can provide these tables if you contact us. Okay, so now we know what is required. So let's see what are the main things to do. The 2 main electrical tests: the ohmic measurement and the capacity testing, which are the true test, the 2 tests that will tell you the most of the information about the battery and some best practices. Remember to submit your questions so we can help you at the end of the session with the panelists that we have here. So feel free to ask. Okay, so ohmic measurement. Every type of battery, every type of construction, we just mentioned the VLA, the VRLA, the NiCad batteries, they will have a characteristic ohmic value. A battery is nothing else than an electric equipment, and any electrical equipment you can model with a network of resistances, capacitances, or inductances. And in this case, there's one model for the battery. We can see it here to the right of the slide. And if you measure across the terminals of this circuit, of course, you're going to get an ohmic value. And it's all we mention, or it's included, or is mentioned in the standard as ohmic value because that will depend on how you measure it. Any method you use to measure it, if you measure under good testing practices, it will allow you to characterize this battery or this cell, and will allow you to trend the value. And any change in the ohmic value is it's a direct indication of the change in the health condition of the cell. So that's why it's a test that is recommended in the standard and the 3 documents that we have for reference, and it's one of the main drivers for action, to take any action on the batteries, because you can evaluate batteries very easily with this. As a general rule of thumb, when the ohmic value increases, when the resistance or the impedance increases, the capacity of the battery will be reduced. However, there's no direct correlation for capacity calculation, so you need to be careful when making conclusions, and you need to investigate further. There's 3 different methods to obtain this ohmic measurement. You can use conductance, you can use resistance, or you can use impedance. And one thing is that the results are not directly comparable. You can use a different frequency in the impedance method, and you're going to get even different results from 2 different type of signals, or the conductance or the resistance. So it's important to define the testing method or the testing technology to always have proper results. To obtain reliable and consistent data, you depend on electrical, chemical, and thermal equilibrium. Basically, the battery has to be fully charged, and this is kind of highlighted in another slide because it's really important to have the battery fully charged. But it has to be under floating conditions for 72 hours after running a full charge or running an equalizing charge, just to obtain this equilibrium. No changes in temperature, a stable temperature, no changes in the current that is used to charge the battery, no changes in the voltage. It has to be pretty stable and fully charged. And that's why the standards recommend 72 hours after adding water or charging the battery in the case of one type or another type of battery. And changing or changes in the floating signal, like increasing current or even a ripple current or noise in the system, will also influence the result. If once you have verified that you don't have any of these issues in your measurement, and you obtain a value, you can determine that there's a degradation when there's a significant change in or a variation or a deviation from a baseline value. And of course, you need some warning or some criteria to define what is high or significant change. So these values are established with the trends that you perform by measuring at the same cell through the time. Every 6 months, after probably 3 measurements, you can start establishing which are going to be your warning limits. We're going to talk about some recommendations about that as well. So specifically talking about the impedance test, which is one of the technologies that you can use, well, it is a test in which you apply a current through the battery. You inject an AC current signal, and with a voltmeter, like basically these two guns here, you can measure the voltage drop across each of the cells due to this current that you are injecting, and measuring that current will give you the two terms of the Ohm's law that can be used or can help you to calculate the ohmic value, in this case an impedance test, an impedance value. This measurement will measure the entire circuit. You are not disregarding the resistances. You are measuring resistance and capacitance, and probably a small inductance that can be there. So you're going to be including all of the circuit. That is the advantage of using AC signal. And another big advantage of this test is that it is an online test. You don't need to remove the battery out of service, or you don't need to take it out of service to be able to perform the test. You just need to be sure it is fully charged. And this test doesn't load or stress the battery. You're not affecting the battery by any means with this test. So it's totally no-sieve test. It won't do anything on your battery, and will give you very good information for to determine the health of the battery, the health condition. And due to the nature of the test and what it is being done when you perform this test, there's the advantage that you can get other values from this test. So in addition to getting the ohmic value, you get the voltage of each cell, the float voltage also of the entire string. You can get the float current of this entire string. You can get the ripple current, and although this is not one of the requirements from NERC, it's a very important parameter, because ripple current can be harmful to your battery. The maximum recommended ripple voltage is 3.5% of the RMS voltage, and the maximum recommended ripple current is 5% of the 8-hour rate discharge of the battery. So exceeding these limits can lead to a generalized elevated temperature in the batteries, and temperature is one of the worst enemies of batteries. So watching out for ripple current is very, very important, and you can trend this value as well when you perform an impedance test. You can measure the strap resistances the same way that you were able to measure a voltage drop across the cell. You can measure the strap resistance by measuring the voltage drop across the strap due to this same current, AC current, that you're applying. And the fact that you are injecting a current throughout the system, and you can measure that current anywhere in the battery, in the string, means that you have battery continuity, which is one of the requirements of NERC. So all of this to say that with one single test, one single shot on each cell, you're going to be able to gather most of the information that is required from NERC, in addition to the ohmic value. And you are also gathering information from another standards that will help you in determining the condition of the battery. As best practices for impedance test, again, be consistent on the use of the instrument and the accessories. This test is highly dependent on the type of instrument that you use and the accessories that you use. Any deviation in the value that you measure, you should investigate that for that deviation comparing to the average, to the string average. If you only have one measurement, you can still start doing some analysis by establishing the average of all the string and comparing to that. You can compare also to historical values, like a previous test or the trend that you have from previous tests. or you can establish a baseline value. And this is, I have it highlighted because it is an important value to calculate, to obtain. It's something that will be dependent on each string, on each cell. And the way to calculate this is from some averaging of good values, which you need to establish or determine when doing your measurements. There's software that can help you to do that, and will establish the baseline value from your measurements that you have been performing. Also, for the best practices, again, the battery should be fully charged. If there's any deviation, again, from the values that you are obtaining previously, you want to verify that the floating signal is not too high, the current signal, the float current is not too high, the battery is not charging at that moment, or that there's no noise or ripple in the system. If there's any instrument change, or if there's any temperature change from the previous measurement. Here in this slide to the right, I have like some examples of what can happen if your battery, let's say if you are using two different instruments, or instruments that are applying two different signals to obtain the result. So you can see in this very first one that instrument A provided this value for each cell, and instrument B gave you these results. It's more than probably 50% of change, and that is, if you are not aware of that you are using a different instrument, you might think you have a problem in the battery. That's one of the consequences of not using the same type of instrument and accessories. And the battery, the charge level of the battery is also important. Here you can see a battery fully charged in red for each cell, and the same battery slightly discharged. It was left without any charging signal for like 1 day or 2 days. It was naturally discharging without any load, and you can start seeing some changes in the impedance values there. So these things will definitely affect your results, so that's why we put them as best practices to always keep them in mind. Below in this table, in this slide, you can see a table where you can get some suggested percentages to use as flags for impedance testing. As I was mentioning before, you can compare within the same test, within one single test, you can compare to the average. So for example, for VLA batteries, it will be 5%. If the cell changes 5% from the average, that kind of triggers an alarm and asks for more investigation. If you have a previous test, you are looking for a change not higher than 2%. And if you have a baseline value, if you already established a baseline value, you are looking for a change not higher than 20% from that baseline value. And here in this slide, you can see the result for each cell graphed in percentage, graphing the change in percentage from the average. So for example, in this slide, in this graph, you will investigate farther for cell number 1, cell number 3, cell number 9. They are really above the average, which is 5% on a VLA battery. So these are the suggested values, the industry suggested values for this type of test. Also, we recommend you to define your own criteria from all of the testing and after really knowing the battery. One advantage is that you might have the same battery across the system, so you can gather a lot of information about the same type of battery or cell, and this will give you very good criteria to define your warning levels. Okay, so the next test is the performance test. The performance test is really a discharge test, a test in which you discharge the battery in a controlled manner with the only purpose of obtaining the capacity of the battery, how much energy the battery can store. The capacity is also the ability of the battery to deliver current at a specified rate. So this means that you need to use a constant current or you need to use a constant power to perform the test. This capacity is a nameplate value. It is expressed in amperes hour. And for example, an 800 amp hour battery means that the battery can deliver 100 amps for 8 hours. Nominal rating is usually 8 hours. There are some other countries or manufacturers that use 10 hours or 5 hours. The most common here in the US is 8 hours. And one thing that you would think is that the battery ratio is linear, that okay, if it can give me 800 amp hours in 8 hours, or 100 amp hours constantly for 8 hours, it might be able to give me 200 amps in 4 hours. But this ratio is not linear. We're going to see a table which shows that. The capacity test, again, is a controlled discharge with a constant current or constant power, and you drive the voltage of the battery to a specified voltage. The manufacturer will indicate what is the minimum voltage that you can discharge the battery to. And as you discharge the battery, when you apply current, the voltage will start dropping, and you will expect the battery to reach this minimum voltage at least at this specified time, like 8 hours or 4 hours. And if the battery doesn't reach that time, it gets to that minimum voltage before completing the specified time, the capacity is reduced, and there's a formula to calculate that value. There's 3 types of tests that you can run to determine the capacity of the battery. You can do an acceptance test, which is basically the test that you run at the beginning of the life of the battery, usually 6 months into the installation of the battery, or at certain point before 2 years of the battery. Then you can run the performance test, which is after 2 years of the battery, to determine if the battery started deteriorating, or how is the capacity behaving on the battery. The modified performance test is another type of test in which you still calculate the capacity. You can get that value, but you also check that the battery is capable to meet the duty cycle that you have in the substation. So there's very specific procedures on how to perform these tests, and they are established in the IEEE standards that we mentioned before in a previous slide, and we encourage you to check those standards, or you can talk to us and we can provide you further information on that. So one thing about the capacity testing is that it is the only test that can get you the true condition of the battery. Impedance testing will give you some, or ohmic values will give you some indication, a very good indication of the health of the battery, but it will never tell you what's the capacity value of the battery. So the discharge test or the capacity testing is the only one that can give you the true condition. And it's probably an overall indication of the string, not of each cell. That is the advantage of the ohmic measurement, that it can tell you what is the condition of each cell. For capacity testing, you need 4 things, or you need the following information. You need the discharge table to be able to get the minimum voltage that you can run the battery to, and there are going to be cases in which you have several minimum voltages for deeper or shallower discharges. You have the temperature. As I mentioned before, temperature is critical for batteries. They should always remain close to this reference temperature indicated in the table of the manufacturer. And then you have the discharge rates. And as you can see, for the example that I was using, this type of battery, or this model is an 800 amp hour battery. So during 8 hours, or you can draw 100 amps constantly during 8 hours. But if you want to replicate, or you want to get the same capacity of this battery in 4 hours, you need to use a different discharge rate. So definitely manufacturer tables are required to be able to perform an accurate test. You will never be able to run an accurate test without this table. With this information, you need to also, once you have all of this information, you need the battery needs to be fully charged and properly maintained. And this is depending on the type of test as well, if it is a modified performance or a performance test. You need the temperature to be able to correct the temperature or the result. There's a correction factor table. And as for the instrument, or what you need to run the tester, is a load bank, something that can do a constant draw of current or power in a very controlled manner, very smooth and controlled way. And this load bank, this resistance bank, also needs some brains to be able to stop the test when it is required, when it reaches the minimum voltage, or depending if you just want to run it for the specified time, you can do that. You can stop the test with voltage limit, time limit, capacity limit. And it is also recommended to measure the individual voltages throughout the test. That is the recommendation, but if you don't have the means to perform a constant and continuous measurement of the voltage throughout the test on each of the cells, the standard asks or requires or suggests to measure at least at the beginning, at the middle of the test, and towards the end of the test. This is how a typical connection will look like. So there's the battery here. You have your positive and negative posts, and you connect the load bank with the brains in it to be able to control the test. You program those parameters obtained from the table before, and you start running the test and just wait for the time to reach the 8 hours or the 4 hours time that you selected, and you're looking for the battery to be able to deliver current during that amount of time. If you are measuring, or there's means, as I said, to measure the voltage on each cell automatically, constantly during the test, this is one of the arrangements. Of course, you need to have something connected to each battery, to each cell, and all of that information will go to the same instrument, so you can have all the information there, and at the end have a result like this. This graph to the left is the discharge curve, how the voltage behaves across or during the time of the discharge, or during all the discharge. And this red line is the limit where the voltage, where the discharge should stop. So in this case, it is a 48 volt battery, which running the discharge down to 1.75 volts in 24 cells, the stop voltage is 42 volts. So this is why we have this red line here. And this test was the program, or was selected to be an 8-hour test. In the end, it ran for like 10 hours and a half. So the capacity obviously is higher than 100%. And you can see that calculation here. The percentage capacity is 133%. Very good result. You were just expecting 100%, but you have 30% more of battery there. So it should, if you keep this battery properly maintained, you will be able to have a very good lifespan in this battery. And as I was saying, this is telling you the true condition of the battery. It's telling you, okay, what is the total amount of capacity that I have. But you don't have a way to determine what if each of the cells are in good condition. This is a combined effort of 24 cells, and as you can see here from the other graph, this bar graph, from the voltage measurements, there's 2 cells that are not performing that good. And if you just perform discharge test, you might not notice this, and especially if you don't measure the voltages across the test, throughout the test, and if you don't do any other confirmation test, you're not going to notice a change in the capacity that fast or that easy. And again, this voltage is here. The full bar indicates the voltage at the beginning of the test. The green or yellow bar shows what was the voltage at the end of the test. The yellow line across the bars is the minimum value, the 1.75. So we see that at the end of the test, the battery still had some voltage there, and basically these 2 cells caused the test to end probably a little bit earlier than what it might have ended if the battery, those 2 cells were in good condition. Still, you have a good battery, but 2 cells are questionable. The way to calculate the capacity is a basic formula. So from the table, you have an expected time, an 8-hour duration or 4-hour duration, depending on what you select. That is this term here, the expected time. And once you run the test, you have the actual time, how long the test lasted. So in this case, for example, in the previous slide, it will be 10 hours and a half here, 8 hours and a half here, and this, 8 hours here, and this term will be the correction factor depending on the temperature at the moment of starting the test. By plugging all of these values here and multiplying that by 100 is that you obtain the capacity. So very basic is the actual time over the expected time and correction factor for temperature. And the table, correction factor table, is provided in the IEEE standard for each of the batteries. It's the same one. So you can use that information to do your calculations. As best practices, well, you want to run the test probably for a time the closest as possible to the duty cycle of your battery, of your substation. This will give you the confirmation of the capacity, and also will tell you if the battery is capable to meet the duty cycle of the substation without running a performance test, a modified performance test, which might be a little bit complicated. For trending purposes, try to use always the same duration. You saw in that table there were options for different times, and this is one of the main things with the capacity testing, that it might be a long test or a resource demanding test. To be able to reach those 200 amps or 150 amps, you might need to use some bigger equipment or more load, so you might not have the resources, so you have to spend more time running the test. And that's why it's a test that it's not that perform that oftenly. In addition, that it affects a little bit the life of the battery. It's one cycle that you're taking out from the battery, but mainly because what it represents, the battery has to be offline. You should not be drawing additional current from the battery, or you need to account for that if you're doing a test online. And most preferred method is to bring a backup system, to bring a trailer with a battery in there, just to be able to have peace of mind with the substation and not risk an additional fault in the system. So deciding the time has many factors involved. So try to always use the same time to be able to trend the values. batteries have an efficiency associated to them, and the higher the current, the lower the efficiency. So you want to try to always use the same time for the discharge. Another thing, when you perform the test at the beginning of the life of the battery, is that you will have capacities ranging from 90 to 110%. In the previous example, you saw it was up to 133%. So it's common to see higher or lower values. And the criteria to replace the battery is when you reach 80% of the capacity. When your result, when that calculation comes out of equal to 80% of the battery or 80% of capacity, that is the moment to replace the battery, and you have, according to the standard, 1 year to do this. Also, an additional recommendation is when you reach 85% of the capacity, you start monitoring the battery closer. You probably increase the periodicity of the testing, so you can try to determine when it is reaching, or if it is reaching faster, the life of the battery. Well, so this concludes the testing portion. Just as a conclusion or recommendations, final recommendations from this presentation. Well, it is really, NERC is really important, battery is really important. They are very important for the system. So you definitely, if you are in one of these entities that need to comply with NERC, definitely you need to implement a battery maintenance program. If you don't need to comply, still it's an asset, a very important asset that you want to maintain. So try to or review or implement or improve your current maintenance programs on batteries using the IEEE, the NERC, and the NETA recommendations. As a minimum, you need to comply. If you are obliged to comply with NERC, you need to follow these minimum requirements indicated in the tables that we showed today. If you need to comply, be prepared. Keep the documentation. It's not just about having the program in place. It's about keeping the information and keeping the records to be able to demonstrate that things are being taken care of. And on the electrical side, the kind of a general statement that you can conclude here is that no single test will provide you the real condition of a battery. So a combination of tests is the best way to determine what is the condition of the battery, and combining these two type of tests, the ohmic measurements and the capacity testing, will give you a very good indication of the condition of the battery. Of course, we have equipment that can perform all of these tests, and as I was mentioning, an impedance tester can give you most of these measurements in the most of these values, or comply with, or these tests that you need to perform. By 2 or by 2P, they can measure the ohmic value, the voltage of each cell, the float voltage, and the current of the entire system. The ripple current, the strap resistances, and you can check battery continuity. There's a smaller instrument called by 3, can give you the same values except the battery continuity. However, you can measure the float current, so that is a confirmation of battery continuity. So it's an indirect battery continuity measurement. For a capacity testing, you can use Torkel 900 or 800 series. You can do performance test, modified performance test, or same capacity testing. And now we have the ability to measure the voltage while the battery is charging back. Some places will have that in their maintenance procedures to see how the voltage is behaving when charging back. So we can do the overall measurement there. We can do the automated measurement on each cell with the VVMs, and this can be during the capacity test or during the charging back the battery. And as mentioned at the beginning, NERC requires you to have all of this information very well documented and very well organized. So we have also a software, PowerDB software, that has default forms, or you can customize your own forms. You can create your own forms for NERC compliance. They can be stored in a database. You can do trending with all the information. It's a great tool to provide asset organization and to keep a track of all of the assets. You have reporting capabilities, and it is a compliance. It has a module called the compliance scheduler, which will help you to determine when battery needs test or any other asset needs to be tested, and when if you are in compliance or not. With this, I have ended my presentation, and now we have Jamie doing the closing statements and opening the question and answer session.
Okay, thank you, Volney. At this time, the webinar is officially concluded. We will now take 30 minutes to answer as many questions as possible. And if you weren't here at the very first, we actually have some panelists today. We have a couple joining us with Volney as well, a couple guys, Robert and Andy with us today. Also, if you have any other questions, if you haven't asked already, you could submit them now into the Q&A box. We do already have probably over 40, 50 questions that were asked. We're going to try to get to as many as possible in 30 minutes. For all those that aren't answered, we will reach out to you by email and have those answered for you, though, within the next couple weeks. For those that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon future webinars. Also, a copy of the presentation will be emailed to all of you in the next few days. A recording of the session will also be available on our website at megger.com/webinars in the next week as well. And our webinar page also contains the schedule for all upcoming webinars as well as recordings of the previous webinars. Okay, and at this time, we'll go ahead and open it up for your questions. And we already have a few that we've picked out. The first one we have today is, their question was, we have an 18-year-old flooded lead acid battery bank. It is on an auto-alarming and monitored system on intentional grounds. We have performed and documented monthly, quarterly, and annual maintenance and testing since new, as well as perform battery cell ohmic impedance testing using a byte 2P. All tests indicate normal and passing conditions. The question is, do we have to perform battery discharge capacity testing?
Okay, and well, I can start answering the question, and probably Andy can help me also with this question. If you have been doing all of these testing, definitely you have been doing things correctly. One thing that I didn't mention at the beginning is that batteries have a definite lifetime span, so they will die, and usually they are designed for 20 years or 10 years, and battery temperature conditions will indicate you or will affect how the life of the battery will behave. And but if you have been keeping them in very good condition, and all of the measurements with byte are not showing any deviation, you might have a good battery still, but anyway, they will die, and 18 years old is pretty close to the end of the life of a battery. I don't know, Andy, if you have something to add there.
Yeah, with the flooded cells, like I said, when you look just at the NERC requirements, purely going on NERC requirements, you can do one or the other. You don't have to do both. Now, if you look at the IEEE, now keep in mind, NERC is dictating the minimum required maintenance. If you look at the IEEE standards, they'll actually suggest you do both. And basically, they recommend doing discharging over a quarter of the period of the battery's lifespan. So if you have a 20-year battery, you would do it every 4 years. I'm sorry, every 5 years. That was good math, huh? But per the NERC requirements, which is the minimum requirements, you are correct. It's just one or the other. But the battery does have a limited lifespan, and with a flooded lead acid cell, typically when it starts approaching end of life, you will see a change of about 50 to 100% on your ohmic tests from the baseline value. That is a typical measurement.
Okay. Think that is that it for that question?
Yes.
All right, I'll go ahead and move on to the next one. Next question, in table 1-4, the last row for the 18th month calendar or 6 calendar maintenance intervals, can you elaborate on how you interpret the end of the first paragraph, which states, verify that the station battery can perform as manufactured by evaluating cell measurements of battery performance against the battery baseline? And they said more specifically, how do you interpret the battery baseline, and can you recommend how to define a proper baseline?
Okay. Baseline is actually one of the most, I would say, misunderstood items that you can get into when you delve into the world of ohmic testing. All baseline is a reference value. It's your starting point, okay? You will hear people say you can go to a battery manufacturer and get a baseline value. And if you look at the VRLA data sheets, you may even see them on there. IEEE does not recommend using those values. The reason is basically because different ohmic testers will provide different values because it's not an absolute measurement, it's a relative measurement. And by that, what I mean is we're comparing the reading we get today to the one we got previously and seeing how much it changed. If I take 3 different ohmic testers, they're going to test using different signals and at different frequencies. So each one, if I measure the same battery with each one, I get 3 different measurements. So you don't know what type of instrument the battery manufacturer used. Also, typically they perform testing on what's called a green battery, meaning it hasn't completed formation yet. When secondary batteries are manufactured, they don't have a charge. They have to be charged or go through formation. Typically, when you receive them, they're green. So they have to actually stay on float for a period of time before they achieve full capacity. All right. So IEEE recommends you establish your own baseline parameters. Ideally, it's after the batteries have been installed and formation has been completed. With a VLA battery, a flooded lead acid, this can be a week or so after they're in and have been fully charged up, equalized, cooled down, and your capacity test has been performed and showing 100% capacity. With a VRLA battery, they're going to need to stay on charge for at least 3 to 6 months before you establish the baseline value. This is to allow any trapped gases to escape and to allow them to fully complete their formation. A gel cell can take up to a year before it's actually fully formated. Now, once you have established baseline, okay, what IEEE recommends is to look at the percentage of change from that baseline on the cells, all right? And they're going to say anything that's considered a serious change should be looked at, all right? They define anything from a 50 to 100% change as a serious change. That's actually in the 1188 standard for the VRLA batteries. And this is also very important. It also depends very much on how critical is the application. And I would also throw in one more thing, because if you're using VLA batteries, one thing to keep in mind is they fail in a different mode than VRLA batteries. VLA batteries, flooded or full of water, their typical failure mode is positive grid corrosion. When they fail, they fail in what's called a shorted mode, meaning current can still pass through them, even if you have one bad battery. So in a critical application, a series string is fine, but if you have a VRLA battery, those fail due to dry out. Okay, they operate in electrically starved mode. So if you have a critical application, those should be in parallel, because if one fails, it fails in what's called an open mode, and current may not be able to get through it. Okay, so when you look at your percentage of change from baseline, like I said, with a flooded lead acid, 50 to 100% is good. But when you start getting to a VRLA, you might want to consider being a little bit more cautious if it's in a critical application and saying 20 to 30%. So I hope that answers that somewhat.
Okay. Thank you, Andy. All right, on to the next question. How do you create a load to perform the discharge test?
So on that one, of course, I recommend using the Torkel, but basically we're just putting a series of resistances together to draw the amount of current out of this. The only thing you need to be aware of is, because we're trying to do either a constant current or a constant power, we have to adjust that resistance level as we go through, because as the voltage drops, we need to adjust the resistance to compensate. So, you know, you just need some kind of resistance bank that will actually adjust. And of course, this is why we manufacture the Torkel to make this a lot easier.
Okay. Thank you, Robert. All right, next question. In Table 1-4B, the 3-year testing, is that a requirement? Is that a requirement if you are doing ohmic testing every 6 months?
Okay, that is quite an interesting question, because it's not very specific in the table. The way we see it is that you need to do every 6 months the ohmic testing, and whenever you hit the 3 calendar testing, you have the option to do ohmic testing or capacity testing. So yes, kind of a straight answer. You still need to do it every 6 months, but where you have the option to select one or the other is every 3 years. And I guess once you start doing one thing, you keep doing that one, and you don't need to change on that.
Okay. Appreciate that, Volney. On to our next question. How is battery continuity verified specifically, and does it require removing the battery from service?
Now, the batteries do not have to be removed from service. If you want to do a direct measurement of battery continuity, now keep in mind what continuity basically is saying that I can get current through this string. Okay, I have a continuous path. So, well, if you're using the byte 2, it's very simple, because when you hook up the transmitter injects a 10 amp signal through the entire string, and it doesn't have to come offline to do that. So that's actually part of that test to do. Okay, that's probably the easiest way to verify that. Otherwise, if you don't do that test, you would have to make the argument that the batteries, if you do a capacity test, they obviously have to have continuity, or they're going to fail that capacity test. And you can also take the argument that if you're doing a full ohmic test, if there's an open somewhere in the string, you're going to find it. Okay, but again, the direct measurement of it is to inject the current directly through the entire string, which is very simple with the byte 2 to do that. It's actually part of the test.
Okay, thank you, Andy. Next question. On the discharge test, what we have to do when one cell has reached the end voltage earlier than the other cells before this test is complete?
So basically, what's going on is you're doing an overall drawdown of all the individual cells, and of course some are going to draw down earlier than others. And so what's important to remember is you don't want to, like as we had in our example, pulling down to 1.75 volts per cell. you don't want to just stop the test when one hits 1.75 volts. You want to hit it when the overall average cell voltage is 1.75. So some, when you stop the test, might be at 1.8, some might be at 1.6, but you want to keep going until basically, you say if you have 60 cells, you have 60 times 1.75. You want to measure the overall battery voltage and keep going until that average cell voltage is 1.75.
Okay, thank you, Robert. On to the next question. For VRLA, if you continue to take ohmic values every 6 months, you are not required to ever do a discharge test, correct?
Okay, this question is similar to the one I answered before. As I said, it's not very specific there. From if you read the table as it is, the interpretation you can give to that is that definitely you need to still do ohmic testing every 6 months, and just every 3 years you define if you want to do ohmic testing or a capacity test. But every 6 months, the way we are seeing it is that you need to still do it every 6 months.
Okay, thank you, Volney. Next question. Our battery chargers have ground detectors. If there are no ground alarms on the charger, is that enough to satisfy the verify for an unintentional ground requirement, or does this have to be verified by a meter?
The actual standard doesn't define exactly how you have to do this. So you have the liberty of defining how you're going to do it. If you have a ground detector, that can be fine. But one thing you have to do is you have to document that you've checked it and that there's no indication of a ground fault. And obviously if you don't have one, you want to double check that, you just take a meter and measure from each side to earth and see if they're equal within the requirements.
Okay, thank you, Andy. Next question, does load bank testing reduce the life of a battery? Some call it destructive in a sense that weaker cells might fail in this test. Please comment.
I'll answer this. So this is like a common question we get, and technically, yes, you are putting a load, you are pulling it down, so it is somewhat destructive to the battery. But these batteries are generally have like at least like a lot of cycles, 1,000 cycles in them or so. I don't know the exact number. So like going back to IEEE, and if it's a 20-year battery and you're going to do this a quarter of the life, each time a quarter of the life, so you're only going to do this test maybe 4 or 5 times over the life of the battery. It really doesn't do that much to the health of the battery, because you can do a lot more discharge cycles. And so it's better to know the true capacity of your battery and that it's actually going to meet the required load. And in the overall scheme of things, the amount that damage you're doing is insignificant to the overall life of the battery, I would say.
All right, thank you, Robert. Okay, next question. As PRC-005 is to keep track of testing schedules and it might get overwhelming on big systems, is there any recommended software that would auto-update and give workflow directly based on the testing date?
Okay, definitely remember this, we just talked about batteries here, and this standard is for protection system. So it really also covers mainly of the main part of the document covers all of the protection system. And as I mentioned before at the beginning of the presentation, it's there's 14 standards, 14 family standards. So yes, it can be overwhelming, and that is kind of a very good reasoning to ask this question. And definitely you need to use a software. Companies they have a database system that they have been using for this, and we as a provider of electrical testing equipment, we also have this software that I talked towards the end of the presentation. It's called PowerDB, and it has a specific module for NERC compliance, which will tell you what is out of schedule or what is next to be tested, what is out of compliance, and will help you to organize all of your testing activities and all of your compliance documents. That's the tool that we can recommend for this PowerDB.
Okay, thanks, Volney. Let's move on to the next question. Where are the values of acceptable ripple current and voltage derived from? Second question, listed in a standard?
Well, yeah, it depends. The ripples actually comes out of the IEEE 450 and 1188 standards. And basically their limitations are 5 amps of ripple current per 100 amp hour capacity of the cell. That is generally because of the heating effects that can cause over time. Now, in reality, if you're using a substation application, to get over that amount, that typically would be a sign of a bad charger. But in other applications like telecom, you could see that actually from the load side as well. You could see that sort of noise from there. Now, as the second half of that, where is the voltage derived from? The voltage, current, ripple current, and voltage. Wait, maybe I'm misunderstanding this. Where are the values of acceptable ripple current and voltage derived from? So I'm not sure if he's talking there about ripple voltage or DC voltage. The acceptable limits for the DC voltage would actually come from the data sheet for the battery. The battery itself is going to, the data sheet itself is going to indicate what the maximum and minimum float values of the battery can be, and these are critical values that have to be maintained. If the value is too high, what you do is you apply extra heat to that battery, heat it up, and you will increase dry out on VRLA batteries and increase positive plate corrosion on flooded batteries. If it's too low, you will partially sulfate the batteries, which will create problems. And again, if you're talking about ripple voltage and ripple current, the most predominant source of that would be the charger. Typically, like I said, in the substation applications, the charger would be your primary culprit. If you saw a very high ripple on big flooded batteries, typically it's going to be a bad rectifier in the charger. But like I said, in telecom applications, you may see things coming from the load at higher frequencies causing that. And that's where a spectrum analyzer can come in handy.
Okay, thank you, Andy. Next question. During the commissioning of a new substation battery bank with 495 amp hours and 59 cells, first capacity test interrupted due to testing equipment tripping. Second capacity is to be performed. Do we need to equalize the battery bank again before doing the capacity test?
So yeah, on this one, you would have to not only first fully charge the battery back up, and then you want to equalize it once again, and the standard requires you to do it 72 hours before performing the testing. And I'll even mention on this one, say, because you want to give every cell an equal starting point. What happened is some cells might have pulled down a little bit more than the others, so you'd rather equalize them all again. And same thing, if you went through and you did a test and you had to jumper out cells and replace them eventually, you'd actually want to go through and recharge and equalize and perform another test on this. So you always want to start off with a fully charged battery and equalized battery before you go through and perform your testing there. The only thing I'd say is if you're, for some reason, your testing equipment did trip, you actually are allowed one stop within your testing for either 10% of the total test time or 6 minutes, whichever is less. And so generally with the testing, we usually end up being 6 minutes. So if you did have that and you could stop it and go through and fix the issue within 6 minutes or 10% of the total time, continue the test if you needed to.
Okay, thank you, Robert. All right, I think we have time for about 2 more questions. Next one is, according to the manufacturer, we have different hours and the current needs to be drawn to access or to assess capacity of battery. What is a NERC recommended value for duration? Is 8 hours the recommended one typically?
Really, NERC doesn't recommend any time. This would be more oriented to what you have in the system. If you have enough time to have a battery out of operation 8 hours, I would definitely recommend running the 8-hour test. Kind of is the nominal the rating, and as I said, batteries might have some efficiency issue there with depending on the level of current that you use, which will obviously impact the time of the test. So you would like to run the 8-hour test, but if you don't have that amount of time, you have more resources, well, the expectation is that the tables from the manufacturer will provide that equivalency in between the discharge time, the discharge current, and the discharge time. And actually, that is something that you might want to verify or confirm running a test for 1 hour and later on running a test for 8 hours and see if you obtain the same capacity. That is something that we are also working on here. We're writing a paper on that. We're going to be presenting that on BATCon, and that is something to confirm with the manufacturer and find out the best time for you the time duration to discharge the battery. But there's no specific recommendation from NERC or from the other standards.
Okay, thanks, Volney. All right, last question before the time is up. Where did you obtain the percentage values for comparison of baseline ohmic readings?
Well, this one, we have been doing this test for a very long time. We have some big experience on this, and after investigation and running different type of tests and looking into tests from customers, we have developed this standard or these values. Probably Andy can elaborate a little bit more on this. He has more experience with this testing.
Yes, those values, those are the recommended starting values, and they are basically based upon our experience and based on several things such as criticality. Is when we look at a flooded battery, a flooded lead-acid VLA, because of the way they fail in a shorted mode, okay? So you can get current through. Now, so IEEE will tell you, 50 to 100% is a significant change in impedance that needs to be investigated, okay? When you look at VRLA batteries, they fail in an open mode. So when they fail, if you don't have a parallel string, you want to be cautious with them. So typically we're looking at 20 to 30% on those. Now IEEE will still tell you that a significant change is 50 to 100%. So again, these are starting values. As you go along with your battery string and you start accumulating data and start trending it, you'll see the patterns and really get much more familiar with it. And you may decide, based on your particular string, to change that. But these are what we found to be very good, solid, and safe starting percentages.
Okay, thanks, guys. Looks like that is all we have time for today. We apologize if we did not get to all of your questions. We did get a lot of questions. Looks like there's about 100 different questions. So all the ones that weren't answered, we will contact you offline and to get those answered for you here in the next week or so. Just want to thank you all for attending. We hope to see you again at one of our next webinars. Next month, on April 21st, we will be presenting Cable Fault Location 202 Advanced Techniques. So we'd love to have you there as well. That's it. Have a great weekend, and please remember to answer the survey if you can. Thank you.